Welcome on this video about complex numbers. And just as an introduction, where we use complex numbers, for example, in electromagnetic field, with here electric field, this axis, and on the imaginary field, there would be the magnetic field, represented with B there. We are going to focus on 4 exercises, which are really important for the exams. First, understanding the different forms of the complex number. Here is the Cartesian form, for example. Here is the polar form. I'm going to explain it in a second. I want you to put this number in polar form. Then the powers, putting the complex number in the power. So 1 plus e to the power of 5, for example. And I want the result in the Cartesian form. So the basic form where you see directly what is the real part and what is the imaginary part. Then I want you to take the roots of a number. So what are the roots? So that z to the power of 6 equal 1. Spoiler, there are 6 of them because here it's to the power of 6. And as a bonus, I saw in the past exams that there was an exercise which was hard in the sense that if you don't know the equation of a circle, you will have problem with it. So those 4 exercises. So for the first exercise, remember we have 3 forms: the Cartesian form, the polar form, and the Euler form. For example, here, if we take 1, 1 here, 1, 1, we could read here that we have this point which is 1, 1. If you look at this, and it's actually 1 real plus e times 1. So this is the exercise. I want you to put it in this form, the polar form. We have r cos theta, theta being the angle we're looking for, plus e sinus theta. And why do we need the polar coordinates? Sometimes it's just easier to represent it as being, okay, I know this length and I know this angle, and then I just get the point. I don't need to know if this amount there plus this amount there. I can just go like that directly. So put this in the polar form. First we need to know r, and then we need to know the angle. R, it's easy because it's the square root of real number squared. So here we have the real part, which is 1 square, plus here we have the imaginary part, which is also 1, which is like 1 plus 1, the root of it, root of 2. And we already have r. So now we are looking at our angle. For that, the easy part is the arctangent of imaginary divided by real part. So it's 1 here divided by 1 plus something. So careful, this is really important. We are looking for the arctan. It's arctan of the imaginary part divided by the real part of the number plus something, depending on where your number is. We had 1 plus e. So we have a positive real part and a positive imaginary part. So we are looking at plus, plus, and we are looking at this part. So we don't have to add anything. We are adding 0. But let's say we had a negative part and a positive in this, then we would be in negative positive. And we would have to add p. This would be like arctan of the angle, part, real part, plus p. And negative, negative, it would be also pi. Positive, negative would be this part. And then we would have to add 2 pi. So we have arctan of 1, p over 4. And then we put it together, and we put that in the polar form. And then we are done. Now, you're probably worrying about remembering those values for p over 3, p over 4, p over 6. I have a way to remember it. It's only one way, that there are many other ways, so you choose the way you can remember. I'm just going to explain the way I'm remembering it. There are 3 angles we should remember. Pi divided by 6, pi divided by 4, pi divided by 3. Because pi divided by 2 and 0 are angles easy to remember for sinus, cosine, tan. I know there would be this value 1/2, square root of 2 divided by 2, and square root of 3 divided by 2. So I know that 1 divided by 2 is smaller than square root of 2 divided by 2, smaller than square root of 3 divided by 2. So I can write it like that. And I do the same on the other side. So basically I just wrote it in the order, because this is smaller than this one is smaller than this one, etc. And the same is here. So cosinus of pi divided by 4 is the same as cosinus of pi divided by 4 is equal to square root of 2 divided by 2. And it's logical enough because this is the middle value that we have to remember. So it's this one. Now we just have to remember the 2 others. And for that, remember that, okay, when I want to look at the cosinus here, of pi divided by 6, I look at this value, and it's gonna be bigger than the sinus that is gonna be this value. So I know that the cosinus of p divided by 6 will be square root of 3 divided by 2, and the sinus of it will be 1 divided by 2. Same thinking for pi divided by 3. I know that the cosinus will be small, but the sinus will be big, so the cosinus will be 1 divided by 2, and the sinus will be square root of 3 divided by 2. Then that is sinus divided by cosinus, and I remember 3 values. The first value is 1 divided by the square root of 3, the second value is 1, and the third value is square root of 3. And I remember it similarly because 1 divided by square root of 3 is smaller than 1, which is smaller than square root of 3. And I remember more easily 1 divided by square root of 3 than square root of 3 divided by 3. Both are the same values. Now, exercise of the blank page. Let's check that you remember them. You put p divided by 6, p divided by 4, p divided by 3, and then you look at what is bigger. So we have then p divided by 3 is square root of 3 divided by 2, square root, cosinus of p divided by 3 is 1/2, and the tangent is square root of 3. This is this angle. And the same for this one, and the same for this one. Second exercise, what is 1 plus y to the power of 5? First step, you write this one in the polar form. Why is it so cool? It's because you can then use the definition of the power. For example, when you have power of a, b to the power of c to the power of d, then it's the same thing because it's a times a times a d times. So it's a to the power of d, and b to the power of this multiplies c d. This is gonna be to the power of 5 because this comes here, and this is gonna to be the power of 5 times p divided by 4. Okay, then I just put it in the polar form, just putting the angle here. 5p divided by 4. I don't know by heart what this thing is, but I know cosinus of pi divided by 4. I'm gonna do a phase change. So the cosinus of the angle, it's minus the cosinus of this angle minus pi. So why is that so? Let's look at this, the cosinus of this angle. If you do plus pi or minus pi, you will get to this angle. You see that the cosinus of this angle, which is here, is minus the cosinus of this angle. And this also works for sinus. Sinus of this angle is minus sinus of the angle minus pi. And I get pi divided by 4 by doing this. So it's minus square root of 2 divided by 2. Same thing for 5 pi divided by 4. And I get also minus square root of 2 divided by 2. So I can put this result here. And then this is just simplification. So you just have to remember that like square root of 2 times square root of 2 is equal to 2. So square root of 2 times square root of 2 here, I can just remove square root of 2 times to the power of 2 here, and then I remove the 2. And then here, if I do square root of 2 times square root of 2 is 2, square root of 2, square root of 2 is 2, so I have at the end 4. That's how I get the result of minus 4i for 1 to plus I to the power of 5. You just have to remember this method for getting 5 pi divided by 4. You can also remember that it's just like that to the power of 5 cos of 5 pi 4 by remembering a formula, but I find it easier to not remember a formula for this one to the power, because the power by itself is not a difficult thing. Let's just look more into this method. So what is the general method to find, for example, stuff like that, cosinus of 2 pi divided by 3? There is mostly one step plus sometimes another step. So first, there's a phase change. So I spoke of it when we had an angle like that. So we just do minus pi, and just we do, don't forget the minus here and the minus here. So minus. You could actually, it's also the same as plus pi. Use the one depending on what you want, because the plus pi or minus pi, we get the same angle minus. And this is useful in this case. Let's say you do minus pi here, you would get 5 pi divided by 3 minus pi. So it would be the same thing as 3 pi divided by 3, which would be 2 pi divided by 3. So then you would go on this step, but it's a bit of a waste of time, so it's better to directly do 2 pi. You would get 6 pi divided by 3, which would be minus pi divided by 3. But here you just have the problem that you have a minus, but it's not that big of a problem. Sometimes then you would have to use the symmetry. The cosinus of an angle, here, it's the same thing as the cosinus of minus this angle. We actually say that this is an even function. And the sinus of an angle is minus, so this is the sinus, is minus the sinus of the other angle. So it's an odd function. Then we get the angle that we wanted. You just have to remember these angles, and then you can just use them to find those. The third one, this is the trickiest one, because you have to remember the de Moivre formula. So let's start. You do that. Okay, the same thing as cos of 0 plus I sinus of 0. Okay, because cosinus of 0 is equal to 1 and sinus of 0 is equal to 0. Okay, then you use the de Moivre formula, which says that the km root of z is this. Two things to remember about this. Z to the power 6, n is equal to 6. So you will have 6 roots. We usually call them from 0 to n minus 1. The nth root of r, cosinus plus e sinus something, and the angle that you have is actually phi, like the new angle, plus 2k pi divided by n. N in our case would be 6. Okay, you can also write it like that if you want. We use this formula. We had 0 as the original angle. We had 2k pi, and we divide by 6. And I just simplify. So I end up with this formula. But this is just the general formula. Now I have to use it for k from 0 to 5. The first root, which is when k is equal to 0, which is equal to 1, because we have cosinus of 0 plus I sinus of 0. When we put a 1 in it, we get cos of pi divided by 3 plus I sinus pi divided by 3. So we get this number. Then 2, then we get this. And then we use, again, same method. Phase 1, the phase change, and then the symmetry. So one phase change, we do minus pi. Then we get something we know. Almost something we know. We just have to use the symmetry that cos minus x is equal to cos x. One thing, don't forget when you do a phase change with minus pi to do a minus before. Okay? Minus before cos and minus before sine. Okay, so then minus becomes plus here. So the result for the second root would be minus 1/2 plus square root of 3 divided by 2 or I. Set 3, it would be minus 1. Set 4, same method. We would end up with minus 1/2 plus minus 3/2 I here. Here we have this example with 5 pi divided by 3. So you could do minus pi and then again minus pi. Minus would be plus. So you can just do it faster by minus 2 pi directly. And then you don't have to change the sign. So when you do minus 2 pi phase change. And then you get this symmetry and you end up with this. Recap for this. We get 6 roots. And we see that the complex roots are conjugated. This is a complex number. This one, 2. This one, this one, this one. And this one are conjugated because the imaginary and the real parts are the same except for the minus before the imaginary part. Here we have plus, here we have minus. And same here. But let's go for the bonus exercise with the fourth one, which is more of a really exam thing that I saw, and I thought it would be important to remember it because we have to know the equation of a circle. The equation of a circle, if you don't remember, it's you have a center. It's x1 and y1, and this is the equation with the center here and the radius. So we would have the center x1, y1 here, and a radius r, and all the numbers that are equally distant to this would be on the circle. So we are looking for the complex number with that verifies that the length is less than 2. So I just did a circle around 0, radius 2, and I could read it directly. There is another way of doing it, is to say that, okay, this means actually that the square root of the real to the square plus the imaginary part to the square less than 2. Then, since this is positive and this is positive, it's equivalent as when I square it, so I square both sides. And then with a bit of working, I'm just saying that a is the same as a minus 0, which is 2, and b is the same as b minus 0, which is 2, to the square. Here I have 2 to the square, which is 4. And then I have the equation of a circle with the center being 0, 0, and the radius being 2. So 2 ways of doing it. And why did I present the second way? Is because we will do something similar with the b. So for the b, we have this. So we have to do the second method because it's not clear right away. So since it is a complex number, there exists a, b, the real part and the imaginary part of r, so that z is equal a plus ib. And I just directly factorize. You can also write I plus ab, and put the b and the 1 together. I get this as the imaginary part and this as a real part. So when I use the definition of this, I get this is the square root of that. And since this is positive, this is positive, I can just square root both of them. And then I get, again, the equation of the circle, a minus 0. And here, plus 1 is the same as minus minus 1. So I get the center being 0 minus 1 here. And the radius 2 here. And the circle. So to compare, here we have the inside of the circle, because it was said inferior 2, but not the border, because it's a strictly inferior. Here it's not strict, we have also the equal, so we have also the border of the circle, and since it's superior, then we have all of the part. So let's recap. We had first the different free forms, then we have the power. Power is being easier than the roots. The roots, we have to remember this formula, the de Moivre formula, and remember that for n equals 6, you have 6 roots. We also so many ways of remembering those values, and the trick to remember these values. And the equation of cycle apparently can be important for the exam. See you on the next video, and all the best for the exam. If you are like me, you have your exam tomorrow.